Hello everyone. In this session, we will discuss the last topic of the MOSFET. The topic is high frequency analysis of FET. That means whenever high frequency signal is given to the FET, how the characteristics of the FET will be varied. How the input characteristics is available for FET as well as how the output characteristics are available for the FET. Okay, so if we applying high frequency to the FET, then we have to discuss the characteristics of the MOSFET. So here, whenever high frequency analysis is analyzed, whenever high frequency analysis comes into the picture of MOSFET, that time stray capacitances stray capacitance have very important role in high frequency analysis of FET. So up to now we discussed about some capacitance, bypass capacitance and input capacitance, output capacitance, all those. But here those are all will be eliminated and stray capacitance will be very important role. So here, what are the stray capacitance? Generally, FET has three terminals: gate, drain, source, and these three terminals have a different potentials. Drain is different potential, gate is differential potential, and source is the differential potential. But due to the different potential differences, it is applied high frequency signal. That's why it has a stray capacitance. Stray capacitance means the capacitance between the gate and drain, and the capacitance between the drain and source, and the capacitance between the gate and the source. So this capacitance is known as GD, that means capacitance between gate and drain. This means CDS, capacitance between the drain and source, and CGS, capacitance between the gate and source. So how these capacitance will be act for the high frequency analysis. So we will look at here. For example, if at low frequency, what happened? At low frequency, what is the frequency? Frequency tends to 0, not 0, tends to 0. What about XC? XC is become infinite. For low frequency, it doesn't allows. Okay, it will be circuit will be acts as the open circuit. No. Next, at high frequency. Then frequency is infinite. For example, assume tends to 0, not infinite, it tends to infinite. Then XC will be 0. How? The relation between the frequency and capacitor reactance is like this: 1 by 2 phi Fc. So tends to 0. So whenever it is tend to infinite, then what is the problem? So whenever Xc is become 0, the problem is, by the above condition, it will not work as amplifier. So it will not be work as an amplifier. So it doesn't work as an amplifier. Why this condition? But what is our intention? Our intention is to make Xc used in high frequency analysis. Our intention is to these capacitive reactances used in high frequency analysis. So that's why we should make some modifications. That's why we should make cutoff frequency. Then by this cutoff frequency, it will be should make a cutoff frequency. So up to some particular frequency it should operate. So low frequency is okay, but in case of high frequencies we should maintain some frequency, that is 1 by 2 phi RC. 1 by 25 RC. For this particular frequency it will operate. So after that this frequency it will not operate. So we should maintain up to this frequency. This is the last point of the frequency. Here C and R values like that. C always should be in picofarad. Picofarad means it should be in 10 power minus 12 farads, and R should be in R should be maintain FH. So to maintain FH we should take the R value. It should be maintain FH maintain. Okay, then it will be operate very perfectly. So high frequency analysis we should operate in the form of 25 RC form. Right. So now we will enter into the high frequency analysis. So in the high frequency analysis, up to now we discussed responsible capacitors are 3 capacitors. Those are CGS and CGD and CDS. So look at here. Here this is the drain terminal, and this is the gate terminal, and this is the source terminal. Here there is a capacitance between, we can make it like this. There is a capacitance between gate and drain. So I will write gate and drain. This is the CGD, and this is the capacitance between gate and source, and the CGS, and there is a capacitance between drain and source. So drain and source, this is the CDC. So we have to connect these. All the input capacitance, this is the input capacitance short circuited, and this is the output capacitance is short circuited. And what about this is the bypass capacitance, this is also short circuited. Whenever it is shorted, there is no use of this resistance. So this resistance may be call it as the redundant resistance. You can call it as the redundant. Okay, so now we should make into the equivalent model. So now AC equivalent model, high frequency model. So high frequency model, right? So look at here just this is the input voltage first. So input voltage we are giving, and input has 2 resistance. So whenever we are doing the equivalent model, so all the DC sources will be off. This will be act as the ground. Okay, by using that we will write this. Okay, yeah. So first we have input source is there. So just take it as the input source, that is VI. So that is the VI, and just observe here we have 2 resistance. R1 is connected to ground and R2 is connected to ground. These parallel combination is there. I will assume this parallel combination is RG. So this parallel combination is the RG. So RG is nothing but R1 parallel R2. So I will take this is the RG, that is nothing but R1 parallel R2. So I will consider this is the gate resistance. Next, what about gate? Here gate is open. It has, just write open, then we will make it to the capacitance. Next, so lastly we will draw about the stray capacitance. So what about next? Drain is connected to drain and source. Between drain and source we have a current source is there, that is, and source is having the ground. So we will write here, this is the drain, this is the drain point, and drain having the connected to ground, sorry, not source. This is connected to source. Source is the point that is nothing but connected to ground. Okay, yes, this is gm vgs, drain current, and we have the internal resistance. We can use that internal resistance, some rd, we will use or not, no problem. Drain have some internal resistance, take it as a small rd, and after that small rd between these resistance, and this rd is connected to ground here. This rd is connected to ground here. So we have the rd here that is connected to ground. So this is the capital rd, and it will give the output v0, output v0. Now we should make the stray capacitance. Stray capacitance, what are those? Like this. So stray capacitance is one capacitance between the gate and source. So we will gate and drain, this is the gate and drain, that is the CGD. The another capacitance between the gate and source, that is the CGS. The another capacitance between the drain and source, so I will write here, this is the drain and source, CDS. Okay, right. And generally when we are dealing with the high frequency models, that time it has input wiring capacitance and output wiring capacitance. So that should be make it like this. So input side we have some wiring capacitance, I will take it as, this is the CWI, and output also having wiring capacitance, that is CW0. This is the input wiring capacitance and output wiring capacitance. So we will write here, those are, and next is CWI, that is input wiring capacitance. Input wiring capacitance. What about CW0? That is the output wiring capacitance. Output wiring capacitance. Okay. Now we will divide into input side and output side. So now we will take the input side of the amplifier. So here the input side of the equivalent model. So what are those for input side? So if you observe the input side is Wi, and it has the gate resistance. Next it has the CGS between gate and source. And if you observe here, but here the capacitance it has combination with the D, so we can modify into the CMI capacitance, mutual input capacitance. How? Look at here. So just input side, the signal is, modification of the signal is like this, that is, this is the input Vi and have input resistance Rg, yes. And next we have CGS between gate and source. So we have the resistance, that is the CGS, that is the CGS. Just write the straight line here, CGS. What about next? So here the input capacitance CWI, this is the CWI. And what about, we can convert the gate and source another capacitance. We have the capacitance here, this capacitance as CMI, but CMI has some modification formula. We can convert input capacitance as CMI, and here we have some point that is connected to ground here. So how can we write the CMI value? CMI value is like this, that is CMI equal to 1 minus voltage gain whole inverse voltage gain inverse into CGD. Okay, we have the gate and drain. So we have the gate and drain. That gate and drain is coming into the gate and source by multiplying this ratio, that is 1 minus voltage gain inverse. So then from this input circuit we will get some, this is the input plus minus. So by doing the modification we will get some frequency. That high frequency is FH1. What is this FH1? FH1 equal to 1 by 2 phi RC. So what is R here? Here R is directly the gate resistance. What about C here? This C means CGS, CWI, CMI. All are in parallel connection. Whenever capacitance are parallelly connected, the total capacitance will be added. That means CGS plus CWI plus CMI. So this is the high frequency for the input side. This is the high frequency for the input side. Next, what about output side? Output side means next we will go for the this side. So next, output side. So we will make it for output side. This is the output side of the MOSFET. So here if you look at the output side here, output side is between drain and source. Output side is between the drain and source. So like this. And initially there is a drain terminal and source terminal is there. Always between drain and source we have the dependent current source, that is GM into VGS. It is depends on the VGS. And next we have the drain resistance parallel with here. So we should take small rd. Sometimes we will remove this small rd because initially it has. And next, what about output side? And we have capital RD parallel with the capital RD. So we will make it capital RD. Capital RD is between drain and source, and generally source is connected to ground here. What about capacitances? We have CDS is one capacitance, CW is second capacitance. So that will write CDS is one capacitance. CDS or CSD both are same. And output side capacitance, CWO is the output side capacitance. And we have the output side, and if you observe here in the circuit we have CGD also. We can convert it into CMO or CM naught. So we will convert this capacitance R as CM naught. Then it will give the output. Then what is this CM naught? The CM naught is mutual capacitance output side. That value is 1 minus voltage gain into CGD. So for this 1 minus voltage gain inverse into CGD, but for this is 1 minus voltage gain into CGD. That is the difference. So from this circuit we will get the high frequency. The high frequency is, formula is, we can take it as FH2. So FH2 is here also the same formula, that is 1 by 2 phi into RC. 1 by 2 phi into RC. Then what is R? This is the R. R value is small r parallel to capital R. So small drain resistance is parallel to capital drain resistance. And what about C capacitance? We have three capacitance, CDS, CWO, CMO. These three capacitance are parallelly connected. That's why the capacitance is, I will write CDS plus CWO. CWO is wiring capacitance, output wiring capacitance. CMO, output mutual capacitance. Okay, so if you observe here, for input side one frequency FH1 is there. What about output side? Output side also we have the another frequency, that is the FH2. So what we have two cutoff frequencies. by the AC analysis, we have two cutoff frequencies. Those are FH1 and FH2. Those FH1 and the FH2. Two frequencies. And which has to select? The question is which has to select as cutoff frequency for the AC analysis. So for this condition, for example, just take a gain. The gain has two cutoff frequencies. Those are like this. So this is the gain and it has two cutoff frequencies. For example, we have a gain like this, and after some frequency gain will be decreases. We have the two, one is point A. We are getting, by doing this we get FH1 is the cutoff frequency at this point, and then we have another point B. For point B we have the cutoff frequency is FH2, that is frequency and the 0. So we have two cutoff frequencies. Which frequency we have to select for the high frequency analysis? That time we should go for FH. FH is minimum of FH1 and FH2. So which is the minimum frequency between FH1 and FH2? That we should select. Understand? So in the problem he given, for high frequency we have two cutoff frequencies, then which has to select? Then you look at those magnitudes, which has the less magnitude, that is our cutoff frequency. So for example, I will be explained here. We have one high frequency, cutoff frequency is 100 kHz, and the another cutoff frequency of is 2 MHz. Then what is the high frequency we should select for the AC analysis? That time the formula is high frequency equal to minimum of FH1 comma FH2. So which is minimum in this? 100 kHz or 2 MHz? We will get FH equal to 100 kHz. 100 kHz is the minimum frequency. Okay, this is the procedure to select the minimum frequency. Okay, so this is about the high frequency analysis of the MOSFET. In the high frequency analysis means it has the stray capacitance, and we should draw the high frequency analysis circuit and high frequency equivalent model. From that we have to analyze the input side and which is high frequency, and we should analyze the output side and which will give the output frequency, and we have two high frequencies and which frequency we have to select, that will be deleted by this frequency. Okay, so this is about high frequency analysis of the MOSFET. Okay, I hope all of you understand the session. Thank you.